Yesterday, I left you guys working on a problem. I'm going to briefly go over solving this problem. We have a partial neutralization. At the halfway point, we determined in the first calculation that we made yesterday that we needed 100 milliliters of our base to neutralize our acid. At this point in the neutralization, we've added 50 milliliters, which is halfway to complete neutralization. It's still just a partial neutralization problem though. We need to look at how many moles of acid we have, how many moles of base we're adding, figure out how much acid is remaining after we've added that much base, and then we can calculate the pH from there. Moles of sodium hydroxide. Find moles, we take molarity times volume in liters, so 0.100 molar times 0.0500 liters, 0.00500 moles. Moles of acid. Molarity is 0.200 molar, volume 0.0500 liters. So we have 0.0100 moles of HNO3. Now we know that we've only added half of the base required to neutralize the acid, so we know that there's going to be excess acid. We know that because the sodium hydroxide reacts with the nitric acid in a 1-to-1 ratio, that if we've added this many moles of sodium hydroxide, that many moles of acid will be neutralized by that amount. So to find out how much acid is remaining, I would subtract the amount of acid that will be neutralized, which is 0.00500 moles. And this will give me 0.00500 moles of acid that is not neutralized. Now that acid that's not neutralized is going to be what affects the pH of the solution. If we want to find pH, we need to know the negative log of the hydronium ion concentration. If we want to find the hydronium ion concentration, we know that it should be equal, because this is a strong acid, to the concentration of the acid. So I'm going to figure out the concentration of the acid. Concentration of HNO3 will be 0.00500 moles of HNO3 divided by the volume. At this point, we've added 50 milliliters to 50 milliliters, so the volume is 0.100 liters. So the concentration of the nitric acid, 0.0500 molar. Which means that the concentration of the hydronium ion is 0.0500 molar, which means we can calculate the pH. pH is equal to the negative log of 0.0500. What is the pH? 1.301. 3 decimal places because all of our values have 3 significant figures. Any questions? All right. Move on to the next problem. What if we add excess? So we reach the point of complete neutralization, and then we continue adding base. Again, we determined that 100 milliliters would be required to completely neutralize this acid solution. We've added now 150 milliliters. So now we're going to have excess base. all of the acid will be neutralized, there will be excess base. If we have excess base, what kind of pH value should we see above 7? So when we calculate for this particular problem, the pH, we should see a pH that is greater than 7. Well, pH is going to be greater than 7 because there's excess base. We need to figure out how much excess base there is, and then really what is the concentration of that excess base so that we can calculate the pH. The problem's going to be solved very similarly to how we solved for the partial neutralization problems, but this time we'll look for how much excess base instead of how much excess acid there is. So we need to find how many moles of base and how many moles of acid we have. Calculate moles, molarity times volume. So 0.100 molar times 0.1500 liters is 0.0150 moles. Point 200 molar times 0.0500 liters, 0.0100 moles. So we can see that because this reacts on a one-to-one ratio, we have plenty of base to react with all of the acid. How much extra sodium hydroxide, if this reacts in a one-to-one ratio, is there? 0.00500 moles of extra base is remaining. Calculate that, 0.0150 moles of base minus the 0.0100 moles that will react will give us 0.00500 moles of NaOH that is excess. Now we can calculate the concentration of that excess base. The concentration of the excess sodium hydroxide can be found by taking moles and dividing it by volume. At this point, what is the volume of the solution if we've added 150 milliliters of base to 50 milliliters of acid? 200 milliliters. So divide by 0.200 liters. The concentration of the sodium hydroxide is 0.0250 molar. Because this is a strong base, what would the concentration then of the hydroxide ions, which is what's making the solution at this point basic or having a pH above 7, what would the concentration of those hydroxide ions be? The strong base, the same, 0.0250 molar. Now, we need to calculate pH. We have hydroxide ion concentration, but we need to find pH. There are two ways that we could go about doing this. Does anyone want to suggest one? We can find the pOH by taking the negative log of the hydroxide ion concentration, and then the pH plus the pOH is equal to 14. We would just plug in 0.0250 here for the hydroxide ion concentration, and then plug the pOH in here to find pH, or what's one other way that we could do this, and I would say this is probably the less popular way. Carolyn? Yeah, we can find the hydronium ion concentration from the hydroxide ion concentration because we know hydroxide times hydronium is 1 times 10 to the minus 14th, and then what will we do? Yep, and that would give us hydronium. And then the pH would be the negative log of the hydronium ion concentration. So either way that you go about doing this, you're going to come up with the same value for the pH. You decide which way you prefer, and go ahead and finish solving. How do you do what one on there? So that you type in your number, then you'll hit log, and then you hit negative, which is right here. And what do we calculate the pH to be? 12.39. I got 8. Does it round to be 8? 12.398. Above 7, which is what we anticipated. So those are the types of problems that you guys will be looking at for a strong acid reacting with a strong base, complete neutralization, partial neutralization, and excess. I don't remember if I mentioned to you guys yesterday, but neutralization reactions are often carried out by a process that's called titration, and this is the lab that you guys will be doing next week. Titration is a lab technique where you generally are using the known quantity of one substance to find an unknown of another substance. Using titration, though, we can track a neutralization reaction. We can start with a solution of acid, and as we add volume of base to that, we can track what the pH looks like. And we can plot this. And we could literally calculate milliliter by milliliter what the pH would be over a reaction. We could literally go into the lab and do this as well. We could take a pH probe, which measures pH. We could add milliliter by milliliter, and we could record the pH. What we calculated in the last couple of problems, well, we calculated the equivalence point. What volume of base had to be added to reach the equivalence point? 100 milliliters. So for us, this volume was 100 milliliters. Now again, it depends on the acid and on the base, on their concentrations, on their volumes. But for our problems that we were just looking at, what was the pH at that point? 7. The equivalence point is when the moles of acid is equal to the moles of base. On a titration curve, it's the point of what they call inflection, where the curve essentially flip-flops. What was the halfway point? How many milliliters was the halfway point? 50. I think somebody said that, I just couldn't quite hear. And what was the pH at that point? 1.301. And we also calculated, I think, at 20 milliliters. And what was the pH at that point? 0.942. You can see that as we start adding base to the acid, the pH does not significantly change until we get to the point of neutralization. The reason for this is that there's a lot of acid, there's a lot of hydrogen ions present initially. As we get closer and closer to that point of neutralization, the number of hydrogen ions is decreased because they're being neutralized by the base. When we've almost reached the point of neutralization, there's very few hydrogen ions remaining in the solution. So any small addition of base is going to significantly then change the pH. all of a sudden we go from having only a few hydrogen ions to now having more hydroxide ions and hydrogen ions, and that pH will shoot up to above 7. We also calculated then at 150, and that was at a pH of 12.398, something like that. So you can see that through these calculations that we're doing, or through an experiment, we can generate one of these curves. I just wanted to introduce you to that. How many of you are taking biochemistry next year? People do a lot with titration curves, so I just want to kind of open that door and expose you to these, because you guys will be generating these and working with these next year quite a bit. Stephanie. Yeah. And oh, and I have a practice test to hand out to you guys. I'll hand that out to you guys right now. And you can see a number of your practice test questions. It asks you something along the lines of, what would the pH be if you added this volume, and then this volume, and then this volume, and then this volume? And so you're going to be working with one equation or one balanced equation and just kind of calculating throughout that titration or that neutralization reaction. This is your last homework set. You have a lab, but this is your last practice test. How many hours?
It's rounded, almost like 247. Yeah. Because I took out, we'll have to finish like, what, 300?
Summer, weekends. Yeah. Guys, I can't hear anything. Either way, it's a lot. Welsa? This would be the picture for a strong acid with a strong base. What if we flipped it? Instead of adding a strong base to the acid, we added an acid to the base. What would the curve look like then? It would start at the top with a high pH, and it would go down. It would essentially be a reflection of that curve there. Morgan. This would be titrating a strong acid with a strong base. This would be titrating a strong base with a strong acid. And so it only depends on what you're adding to what. So in our practice problem, we were adding the base to the acid, and we were calculating the pH after we had added certain portions of base. If we were calculating the pH after we added an acid to a base, we'd start at a high pH because the base would have a pH greater than 7, and then it would decrease over the course. We would still see the equivalence point. The equivalence point would still be at a pH of 7 because it's a strong base and a strong acid still, but it would start high and then go low. All right. On to then our next set of problems, a weak acid with a strong base. The salt will affect the pH of the neutralized solution, and the neutralized solution will have a pH greater than 7. The cation of the salt comes from a strong base and is therefore a weak conjugate acid. It will not react with water. So the cation will not affect the pH of the solution, just as we saw in the previous set. But the anion coming from a weak acid will be a strong conjugate base and will therefore be able to react with water. Because it acts as a base, it will produce a basic solution at the point of neutralization. initially I had planned on going more quickly through yesterday's problems and today's problems, and then using tomorrow as a day for catch up for those of you who missed yesterday or today. But because I have these videos that I'll be posting, I can take the time to go a little bit slower. So tomorrow I will finish up with a weak acid and strong base neutralization, and then you guys will have a little bit of work time to kind of practice some of these problems. So consider a neutralization reaction between sodium hydroxide and acetic acid. Now I'm aware that it says across the top of the page this is a weak acid and a strong base, but you will not have those kind of labels on your practice test or on your test. We know sodium hydroxide is a strong base because it's a hydroxide containing compound. Acetic acid is not in the list of 4 strong acids that I've asked you to memorize. That's how we know that we have a strong base reacting with a weak acid. So let's write the reaction. Sodium hydroxide, NaOH, is reacting with acetic acid. And I'm going to write this as CH3COOH. So we talked about how we'll sometimes see acids with the H at the end here if they have that COO. The double replacement reaction, the cations will switch places. So sodium and the hydrogen ion, which is written here, will switch places. So sodium will be paired with acetate, CH3COO, and hydrogen with hydroxide. So here's our salt. Let's take a look at the cation and the anion in this salt. The cation, which is a conjugate acid, comes from sodium hydroxide, which is a strong base. That makes this conjugate acid weak. The anion, the acetate ion, is a conjugate base. It comes from acetic acid, which is a weak acid, which makes this conjugate strong. Because this is a strong conjugate base, it can actually affect the pH of the solution at the point of neutralization. We'll take a look at how. Let's look at first calculating how much sodium hydroxide would be required to completely neutralize 50 milliliters of 0.100 molar acetic acid, and what the pH of the solution would be. We know the pH should be what? Based on the fact that this is a weak acid and a strong base, and we're talking about the point of complete neutralization. For a strong acid, strong base, yes. What did we just take down in our notes about when we have a weak acid and a strong base? Should be greater than 7. So we know the pH should be above 7 because we have that conjugate base that's going to affect the solution. Well, talk about that in a minute. Let's first look at calculating how much sodium hydroxide we need to neutralize the acetic acid. Well, just like we calculated yesterday, we need to figure out how many moles of acid we have. We can use that to figure out how many moles of base we need. We can use that to figure out the volume of sodium hydroxide. So moles of CH3COOH. 0.100 molar times 0.0500 liters equal to 0.00500 moles of acid. Now neutralization occurs, remember, when moles of acid equals moles of base. This is how many moles of acid I have. I can use that then in the balance equation to find out how many moles of base I would need. So 0.00500 moles for every 1 mole of acetic acid, I need, according to the balance equation, 1 mole of sodium hydroxide. So I need 0.00500 moles of sodium hydroxide. If I know the moles of sodium hydroxide and the molarity of sodium hydroxide, how can I find volume? Volume is equal to moles divided by molarity. So 0.00500 moles of sodium hydroxide divided by the molarity of sodium hydroxide, which in this case is a 0.100 molar solution. So this will give me 0.0500 liters of sodium hydroxide, which is equivalent to 50.0 milliliters. So we need 50 milliliters of sodium hydroxide to neutralize the acetic acid solution. Now we want to know what the pH will be. Well, if we've added 50 milliliters of sodium hydroxide to 50 milliliters of acetic acid, at this point, we'll have our salt and water. Okay? There won't be any sodium hydroxide, there won't be any acid, because they'll have completely reacted with one another. We'll just have our salt and water. Now, the acetate ion can react with the water because it's a conjugate base, and that's what will affect the pH at this point of the solution. So the acetate ion will react with the water. This is a conjugate base. It will act as a base. Bases accept hydrogen ions. It will accept a hydrogen ion from the water, forming CH3COOH and hydroxide ions. And this right here, the fact that when this reacts with water, hydroxide ions will be formed, is why the solution is slightly basic as a point of complete neutralization. So we need to figure out the concentration of hydroxide ions so that we can figure out the pH. Well, we could do that using a nice table. And you thought you didn't need to know those anymore. If 0.00500 moles of acetic acid is reacted, because this is a complete neutralization, won't an equal number of moles of the acetate ion form because it's a 1-to-1 ratio? So at the point of complete neutralization, I will have 0.00500 moles of the acetate ion. I need to know concentration, though, for this ice table. What concentration, what volume will this be in at the point of complete neutralization? I will have had to add 50 milliliters of base to the 50 milliliters of acid. 100. So divide by 0.100 liters is 0.0500 molar. So once the acid has completely neutralized the base, I have a 0.5 molar solution of acetate ions that can react with water, that can form the acid and hydroxide ions, which is what affects the pH. So once the acids completely react with the base and I have my salt and water, I would have 0 of these initially, so 0 molar. I don't care about the water because it's not part of the equilibrium constant expression. This is going to react, so it'll decrease by some amount when it reacts with the water. This is going to increase by some amount. This is going to increase by some amount. So at equilibrium, I will have 0.0500 molar minus X, X, and X. Because this is acting as a base, I can write a Kb expression for this. Kb is equal to the concentration of CH3COOH times the concentration of OH minus divided by the concentration of CH3COO minus. Now, if I knew Kb for the acetate ion, I could plug that in, right? And I could plug in X and 0.05 minus X and solve for X. And once I have X, I have the hydroxide ion concentration. Commonly, though, we won't be given Kb, or Kb will be a tougher value for us to look up. What we will commonly be given is something like the Ka for acetic acid. And this is 1.8 times 10 to the minus 5th. So for this acting as an acid and producing this conjugate base, we know the Ka. What we can do is we can calculate Kb, though, because Kb times the Ka for any acid and its conjugate will always be 1 times 10 to the minus 14. So I can use this, and knowing Ka for acetic acid, I can find Kb for the conjugate base, the acetate ion. So Kb times 1.8 times 10 to the minus 5th is equal to 1 times 10 to the minus 14. And I get that Kb is 5.555 repeated, so 6 times 10 to the minus 10. All right, perfect. Now I can substitute that in for Kb here. So 5.5556 times 10 to the minus 10 is equal to X times X divided by, because Kb is really small, what can I assume about this X value here? Like subtracting 0, so divided by 0.05. 0, 0. And then I just need to solve for X. What's that? Times both sides by 0.0500, and then do what, Rob? And then square root. And what did you calculate X to be? Oh. Anyone calculate X? Lauren? I got 5.2704. Is that what you got? Check and see how many digits you used. If you don't have at least 4 or 5 digits here, 4, 6 times 10 to the minus 6 molar is what X is. Okay, well, great. Then we know the hydroxide ion concentration, and just like we did in the previous problem, we can find the pH. But guys, has anybody realized that this is a lot of extra work? Why? Why is this a ton of extra work that we don't have to do to solve this? Today's the day you start hating me. This is acting as a base, right? Is it a strong base? It's a weak base, right? It's a strong conjugate base, but it's not a hydroxide-containing compound, right? So it's classified as a weak base. So for a weak base, how can we find the hydroxide ion concentration? Square root of the base concentration times Kb. So before we ever even went through the ice table, didn't we have the base concentration? And we would have still do this little side calculation here. But we have Kb. If you type in 0.0500 molar times 5.5556 times 10 to the minus 10th, take the square root of that, you'll get this exact same thing. Oh, we have those equations for a reason. If you think about what you have really nice shortcut equations to use. So use them. You could, if you wanted to, go through the whole ice table. You'll still get the same answer. I know, I kind of like the ice table thing. I enjoy the problem solving. All right, so regardless, we know the hydroxide ion concentration then, which is X, is 5.27046 times 10 to the minus 6 molar. We have two directions we can go with this. We can use this to calculate pOH. Your attention, please. And then we can use this to calculate pH. Or we can use this to calculate hydronium ion concentration. And then use that to calculate pH. So you choose which way you prefer, but either way, you can solve this. And what do we get for the pH? 8 point something, I think. 8.722. Slightly basic, just like we had predicted, because we have that conjugate base in the salt. What if I told you even that's a lot of extra work? I know, I'm killing you. But if you don't know where it comes from and you just know how to plug into an equation, most of you will get the wrong answers. Most of the time. How many of you struggle a lot with math? And the reason why a lot of you struggle with math is because you're told this is how to do it and this is the steps or this is the equation or whatever, and you have no idea why. So you have no idea when to use the equations and when not to, and how to use them and how to change them, because you have no idea really why you're doing what you're doing. That's why I do my teaching like this. I show you you can use this equation when this happens, so if you start to do the work, you realize when you can and can't use those equations. So, we can calculate the pH for a weak acid, strong base solution, using this equation. Yes, Robert. Well, you couldn't use that on the test. This is the only new equation in addition to that. Okay, so pH is equal to, what does P stand for? Negative log of the Ka. which is 1.8 times 10 to the minus fifth, plus the log of the negative ion concentration, which we determined to be the negative ion concentration that was formed. We determined that to be 0.0500 molar, divided by 0.0500 molar, divided by the concentration of the acid produced on that, which is X. So you would still have to use this equation to find what X is. X is equal to the hydroxide ion concentration, though, so you would only have to plug in here to calculate that. So down here we put 5.2704, whatever that is, times 10 to the negative 6 molar. What is that answer? Type that in your calculator. Yep, A minus is the concentration of the anion, which we determined by that idea of if all of this reacts, this is how much of this will form. And then HA we determined because it's equal to the hydroxide ion concentration according to that little mini reaction we wrote. What is this? Answer. 8.722. This is called the Henderson-Hasselbalch equation. I will refer to it as that equation. I'm not going to try to spell it because I know I'd spell it wrong on the board. But the Henderson-Hasselbalch equation, and I will show you how to apply this to weak acid, strong base neutralization problems further tomorrow, because I realized that some of you are kind of like, well, where did she get these numbers from? Where do those numbers come into play? I would like you to, because we have 7 minutes, I would like you to copy this problem down so we can start here tomorrow right away.